Hi, I'm Professor Goins, and welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in pretty much any college mathematics course, please consider subscribing and then checking out our playlists, watching our videos, and then liking, commenting, sharing those videos. Those are all things that are easy and free on your behalf, but they do help us grow, which would be greatly appreciated. Okay, so let's get into the current video. I want to take a look at the boundary of a set in a general topological space. We'll take a look at some examples that should be familiar to you from, say, the real line and the usual topology, and then we'll look at, say, a set that is finite, and then we'll put a topology on it. We'll find a boundary of something there, which again isn't really going to be very intuitive, but it does allow us to work with the definitions and practice with the constructing those types of things. So the boundary of a set. First and foremost, before I continue, I will be making use of the closure of a set. If you're not sure what the closure of a set is, please watch those videos that I posted on, one, the closure of a set in the topological space, and then two, proving some properties of closures. You really don't necessarily need the second video, but it would kind of add a little bit of insight. But first and foremost, you do need to know what the closure of a set is to be able to follow along with this current video. Let me give you the definition of the boundary of a set. The boundary of a set A in a topological space x tau is given by the following. Okay. Well, one way I'm going to write this is, before I write it, mathematicians are in love with the partial derivative d. So we just use that here just because we want to. The partial derivative, again, it's not a partial derivative, but the notation is the boundary of A. Okay? The boundary of A is given by, what I do is I take the closure of A and then I intersect it with the complement of the closure of the complement. Take the closure of a set, and then I take the so I've got the closure of a set, and then I take the complement of that set A, take its closure, and then I intersect those two. That gives me the boundary of a set. Now, alternatively, the boundary of a set A, we can write it in terms of set builder notation. This is going to be the set of elements X with the following properties. For every open set for every open set where X is an element of U intersects the set A and U intersects the complement. Okay. Depending on what textbook you use, you might see one of those two examples, or one of those two definitions, if not both. What I'm going to do is I'm going to use the first definition as more of a constructive, the definition where I'm actually able to construct boundaries, and then what we can do is we can just check to see if the second definition does actually, if what I come up with for the boundary does satisfy the second definition. This isn't very constructive here, and then especially when I do something like a topological space where the underlying set is finite, and I just give you a finite topology on that, and I just start constructing the boundary from that. This isn't a very workable, constructive definition, but it will be illustrative of the concepts as we go through. This right here is going to be the main thing that we're going to use. So first and foremost, let's look at a definition or an example within the context of the real line with the usual topology. And let's say my set A is given by 0, 1. So the half open interval from 0 to 1 where 0 is included and 1 is not. Now, even without taking a topology course, even back in a calculus course, or possibly an algebra course, if I said, what's the boundary of this? You would intuitively say, or I would anticipate that you would intuitively say, it'd be the set consisting of 0 and 1, which would be the endpoints of that. And you would be correct, but let's go through the definition of this. If I take the boundary of this, it's going to be the closure of A intersected with, well, I take the complement of A and then I take the closure of that. Well, these are actually things we can find. The closure of 0 to 1 would be the closed interval from 0 to 1. And then I'm going to intersect that with, well, a complement. So on the real line, the complement of 0 to 1 will be minus infinity up to 0, union 1 to infinity. And then again, take that closure. And this would be 0 to 1. Suppose I should also group that together. Now, if I take the closure of that, I'm going to get minus infinity to 0, union 1 to infinity. Now, when I intersect those two, well, what's common? The only thing that's common within this interval here and then the union would be the points 0 and 1. And therefore, the boundary of A is, in fact, the point 0, 1, which is what we had anticipated. Now, what I also want to do is let's take a look at the boundary of this exact same set, but let's put it in terms of the second definition here. Well, if I look at the interval, let's say, so again, I'm going to include 0. I'm going to exclude 1. And again, it's going to be scribble in between. So of course, the sketch of this set A and the real line is given by this interval right here. And let's look at it in the context of the second definition that is, again, less workable, but for theoretical purposes, it is useful. The boundary of A is the set X, which consists of the following points. X where, for every open set or for every open neighborhood of X, that open neighborhood or open set not only intersects the original set A, but also a complement. Well, we know that the boundary consists of the points 0 and 1. So what does that mean in terms of these open sets? Well, if I take an open set that contains the point 1, and again, in the real line with the usual topology, let's take a open interval. Let's say go from here to here. Okay, so there's going to be my open set U, which contains X. Notice that this interval, this open set between these parentheses here, not only contains points of A, but of points of the complement. And that's exactly what this definition says. It contains points of A and the complement. Now, of course, I could maybe take a smaller open interval, as long as it contains the point 1, that's going to also meet A and a complement. Same thing over here with the point 0. Take any open interval that contains the point 0. It's going to contain points of A along with the complement, and therefore, and again, it doesn't matter how small I take this interval or how small I take these intervals or big, I will contain points of A along with a complement, and that's exactly the context of the second definition. Now what I want to do is let me clean this up, and I'm going to set up an example for a topological space with a finite set X, and then we're actually going to construct a boundary. Now what's nice about this one is this is intuitive, it's workable. The second example, it's not going to be intuitive, but it's going to be even more workable, or it's going to be workable as well, that I can just construct the set A, its closure, the complement, its closure, and it might be, give us a non-intuitive result. Let's go ahead and take a look at that. Here's my topological space. X consists of the elements the integers 1 through 7, and my topology is given by the following list of open sets. And what I want to do is, within this context, I want to find the boundary of the set 2, 4, 6. Now, again, if I said make a guess, I mean, what would you, I mean, I guess there's finitely many options that you could pick, but 2, 4, 6, what would it even be? Am I going to add anything to this? How, why, where does that come from? Well, let's take a look again just at the definition. Remember that the boundary of a set A is given by the closure of A intersected with the closure of the complement. Now, those are all things that we can construct. I can construct the closure, I can construct the complement, and then its closure, and then intersection. So those are all very, very simple set theoretic things I can do. Let's go ahead and do that. Well, what is the closure of A? Well, again, I'm going to need to know what all the closed sets are. Let's go ahead and list the closed sets. Okay. Closed sets in this case would be, let's try to figure out what color I could use here. I think I've already used, all right, the empty set and X, and then the complement of this, okay, complement, and the complement here, complement, so 1, 2, 4, and 5, and here complement would be 2, 4, 5, complement here would be 1, 4, 5, the complement here would be 4, 5. Okay, so those are all my closed sets. Now, what would the closure of A be? Right. The closure of A, again, is the intersection of all closed supersets of A, which would be 2, 4, 6. What I'll do is I'll take a look at all of these sets here, everything that has 2, 4, and 6, and then I will intersect them. Well, X, of course, has everything. The second one here has 2, 4, and 6. That has got 4 and 6, but not 2, 4, 6, but not 2, 2, 4, but no 6, so on and so forth. Therefore, the closure of A would be 2, 3, 4, 5, 6, and 7. And if I take a complement, that would be 1, 3, 5, and 7, so all the odd numbers. And then if I take the closure of the complement, this would be the intersection of all closed supersets of the complement. And what does that consist of? Well, let's see, so 1, 3, 5, and 7. That would just be X itself. So the closure of the complement will be X itself, and therefore the boundary of A would be the intersection of those two, which would be 2, 3, 4, 5, 6, and 7. That would be the boundary of A. Just using the constructive definition that I started with. But now let's take a look at the second example just to see if that makes sense. So the idea is, if I take any element of the boundary, okay, so take an element of the boundary, let's say 2. Now I'm going to look at every open set that contains 2. That open set would have to have points of A and a complement. So let's go back through the open sets. 2, 3. Well, 2 is an A, 3 is in the complement. 1, 2, 3. 2 is an A, and 1 and 3 are in the complement. The last set here, 2, 3, 6, 7. 2 is an A, 3, 7 are in the complement. And I can do that with every single element here. Let me just pick one more, and then I'll just pick a random set just to verify that it works. Let's take the element 5 that is in the boundary of the set A. So what that means is every open set that contains 5 must have points of both A and A complement. So let's pick see which open set has 5. Well, I guess it was just the entire set X. So let's pick a different one. Let's pick 7. 7, and then let's take the set 3, 6, 7. Well, 3 and 7 are in the complement, and 6 is in A. Therefore, we can see that it will satisfy the second definition as well. Okay. Anyway, thank you for watching, and please consider subscribing.